These are the 4 cards that can be drawn. I draw 1 card, show it, put it back, and draw again. Over many rounds, card 0 appears half the time. Card 1 appears 1/4 of the time. Cards 2 and 3 each appear 1/8 of the time. That is the drawing rule for our game. Before every draw, 2 forecasters write down a probability for each card. Forecast P copies the drawing chances we just saw. Forecast Q is bolder. It assigns 70% to card 0, 20% to card 1, 9% to card 2, and 1% to card 3. Both forecasters still choose card 0 as the most likely card. We score more than the top choice. Start with the whole bar on screen. Have it once. The remaining half receives a score of 1 ideal bit. Have it again to reach 1/4 and add a second ideal bit. Have it once more to reach 1/8 and add a third ideal bit. Each having adds 1 ideal bit to the score. Here is a compact way to calculate the same score. Take the base 2 logarithm of the written probability and change its sign. This calculation also works between exact halves. A 1% forecast receives about 6.644 ideal bits. That decimal is a score. It does not mean that we ask 6.644 literal questions about 1 card. Which forecast will have the smaller average bill over many draws, forecast P or forecast Q? Lock in your answer now.
I choose forecast Q. Card 0 appears most often, and forecast Q makes that card especially cheap.
First, card 0 is drawn. Forecast P gave it probability 1/2, so the bill is 1 ideal bit. Forecast Q gave it probability 7/10, so the bill is about 0.515 bits. Forecast Q saves almost half a bit on this round. The student's prediction is winning so far. Now card 3 is drawn. Forecast P gave it probability 1/8, so its bill is 3 bits. Forecast Q gave it probability 1/100th. That bill is about 6.644 bits. The bold forecast saved a little on card 0, but its near impossible card is very expensive when that card actually appears.
So 1 common card does not settle the contest. We must include every card and how often it is drawn.
That is correct. These 2 rounds are only examples. To score repeated play, we need the average bill implied by the full drawing rule. Start with card 0. Multiply its bill under forecast Q by the chance that card 0 is actually drawn. 1/2 times about 0.515 gives a contribution of about 0.258 bits per draw. Now do the same for cards 1, 2, and 3. The true drawing chance supplies the weight in every row. Card 3 therefore gets weight 1/8, even though forecast Q gave it probability 1/100th. Add the 4 weighted bills. Forecast Q costs about 2.102 ideal bits per draw on this game. Now that we understand the action, we can name it. This probability-weighted average surprise bill is the cross-entropy of the actual drawing rule evaluated using forecast Q. These decimals are scores, not literal message lengths for 1 card. If we turn many draws into 1 long bit message, a good method can approach this average length. Now compute the average bill from forecast P. Card 0 contributes 1/2 bit. Card 1 contributes 1/2 bit. Cards 2 and 3 each contribute 3/8 of a bit. Add those 4 contributions to get 1.75 bits per draw. Forecast Q costs 2.102 bits per draw. The smaller average belongs to forecast P. Forecast P copies the drawing rule exactly. The average surprise bill produced by that matching forecast has a name, the entropy of the drawing rule. Here, the entropy is 1.75 bits per draw. Subtract the 1.75-bit baseline from the average under forecast Q. The remaining 0.352 bits per draw come from using the wrong probabilities. This expected extra bill is the Kullback-Leibler divergence from the actual drawing rule to forecast Q. In words, cross-entropy equals entropy plus the extra cost caused by the mismatch. A general theorem proves that the average mismatch cost cannot be negative. It becomes 0 only when the forecast agrees with the drawing rule for every card that can appear. That is why the matching forecast gives the lowest possible average bill. Our card game illustrates the result, but this one example is not the proof. So far, forecast P matched the drawing rule, while forecast Q supplied the bills we averaged. The mismatch cost was about 0.352 bits per draw. For a new game, let the probabilities from forecast Q control the draws and use the probabilities from forecast P to supply the bills. We switched the jobs of the two forecasts. Will the extra costs stay the same or will it change? Make your prediction now.
I predict the cost will stay the same. We are still comparing the same two probability lists.
The cost changes to about 0.196 bits per draw. The reason is concrete. The probabilities from forecast Q now control how often each card's bill is counted. Reversing the jobs changes the weights. Kullback-Leibler divergence has a direction. Unlike an ordinary distance, its value can depend on which probability list comes first. A wrong forecast costs extra average bits because it assigns the wrong probability to each possible card. Those probabilities describe what we expect before seeing evidence. Next, we will ask how much one visible clue can change what remains uncertain.